Welcome everyone. I'm Danette Allen, head of the Autonomy Incubator here at NASA Langley Research Center. I'd like to welcome you to the third and final installment of our summer 2016 student exit presentations. Today we have Meghan Chandarana and Erica Mezeros, who will be presenting jointly the work that they've done. It has been cooperative and they've made quite a bit of progress on some natural interaction approaches we have for mission planning and trajectory planning. Meghan's been with us now 2 semesters. She was here with us last summer and is with us from Carnegie Mellon University. Erica has also been with us 2 semesters. She was with us last semester, and we were very lucky that she was able to stay with us for another semester to continue the great work that she's doing in speech recognition. But we'll start today with Meghan, who will talk about gesture recognition, and then they'll both talk jointly about the natural interaction techniques that we're using. So Meghan, take it away.
Thank you. Okay, so today we'll be presenting the work, as Nanette mentioned, on our natural language interface for UAV interaction. So this is a quick outline of the presentation. So I'm going to start with the objective of the work, talk a little bit about the motivation behind why this is interesting, run you through what we're calling the holy grail of this type of system, and we'll explain what the acronym means, give you a quick introduction of the system, and then talk you through both the gesture node and the speech node, and then talk about how we integrate those things with our interpreter node, and then go through some of the user studies that we did this summer, including the mouse gesture, the mouse speech, and then the multimodal user study that we did, and then end with some conclusions, talk about some future work, and then talk about some acknowledgements at the end. So the objective of this work is to develop a natural language interface for which non-expert users, so people who may not necessarily have any of the necessary background to fly a complicated UAV system, and we want them to be able to define complete flight paths using the system that we've generated for autonomous UAVs. So they can do this in several ways. They can do things like point-to-point, so they can say, like, I want you to go from here to the back 40, or they can go ahead and define formations similar to the one that you see in the picture on the right, so they can kind of say, like, a spiral and say, like, I want to spiral up to some altitude, and like maybe they want to take measurements along the way as they're spiraling up to that altitude. So this type of system has several requirements. The first is, as I mentioned, that we want an intuitive natural interaction for the system. So this would be similar to how someone is speaking to another person. So similar to how I'm presenting now is that we want to ensure that the user can go ahead and gesticulate and use speech in a way that they would naturally. And so as part of this, we want to ensure that the interface flow is transparent and easy enough to use. And the way that we do this is by providing ample feedback for the user along the way as they're defining these complete flight paths. And as I mentioned, because these are non-expert users, we want to allow them to do this in a way where they're able to take more of a mission management role and kind of abstract themselves away from the low-level system architecture required to run such a complicated UAV system. So now that we know the objective, let's talk a little bit about why this would be interesting or what type of application we could use this for. So one that we like to talk about a lot is an atmospheric science mission. So if you see the picture on the right, imagine that you are an atmospheric scientist and you're out in the field that looks like this. And say you can't necessarily see all of your environment, and so what we do is we augment maybe a virtual map of our environment, which you see in the bottom left of that image. And maybe you're able to use our natural language system to define an initial flight path. And so you can go ahead and depict this flight path both in the smaller map that you see on the left and in the actual environment which you see here. And maybe you have multiple vehicles and you're able to see what kind of real-time sensor information these vehicles are taking. And then you want to go ahead and allow the user to do some kind of management where maybe they see something interesting and they want to tell some additional UAVs to go to that area and maybe take some kind of map of that area or take additional sensor information. So that's sort of what we're pointing to. And what we are assuming is that our vehicles will individually be having their own sensor payload. So they're able to do things that you wouldn't previously be able to do, where say you want to take correlative data and you want to be able to do this with any number of vehicles that you have available to you. So just to re-emphasize the different parameters of this type of mission, our atmospheric scientist or user is interested in flying what could possibly be multiple vehicles, but for this work we're right now assuming a single vehicle for simplicity, and they want to be able to take correlative data if possible with these vehicles and these different sensors, and they want to ensure that the interface is intuitive for them because, as I mentioned, they're not experts and they don't really care what it takes to fly a UAV. All they care about is that they want the UAV to move to the area of interest and do whatever they want at that area. And in order to do this, we want to ensure that they do not have to understand the low-level system architecture, and that's one of the main goals of this system. So this slide shows you what we're calling the Holy Grail demo. So as you can see, I'm defining our flight path with both the speech and gesture system. Then afterwards, you can see the path that I developed in 3D, and this is overlaid over Langley, and you can see a risk map. So that risk map was used to determine the optimal path through our environment such that we avoided obstacles, we avoided areas of high risk. And then after we do that and we provide validation to our user in virtual reality, we can go ahead and fly the mission right away, which is what you see in the video. So in this mission, we flew from here to the back 40, flew forward left when we got there, and a spiral up, and then we landed as soon as we were done with that. So what exactly is Holy Grail and what does it stand for? So Holy Grail is a system that we have, and what it is the human-operated language-based intuitive interface with a gesture recognition applied in an immersive, lifelike environment. So what is included in this Holy Grail system, and what does it take to actually create the demo that you saw on the previous slide? So there are several components to this system. The first is the natural language component, and then we have an interpreter node which takes the gesture and speech information, puts them together in a great way, and then sends that information down to the trajectory generation folks, which can actually use the risk assessment map that we have and generate the trajectory that you saw in the previous image. Those folks are then able to take that information, send it to our VR module, which is able to display the information back to the user and provide feedback. And once the user is happy with that, the trajectory generation folks can go ahead and send that information to the vehicle controller and go ahead and fly it on the actual vehicle. So what Erica and I are responsible for is this natural language node that you see here in Holy Grail. So my part of the natural language node is the gesture part, and both the speech and gesture sort of feed information into three types of modules that we have. So one is the optimization module, and this is things like our point-to-point. How do I get from here to the back 40 without giving any other information about how the vehicle should fly? So we take into account information like obstacles in the way, risks that could be there, and we have an intern who created a risk assessment map for us where we can plan a low risk path between two locations given this map and the risk values. And then formation is what most of you did in our user studies this summer. So how do I tell my vehicle that once I get to the back 40, how do I define that I want it to fly forward right followed by a spiral? That's what the formation part does. And then we have this part called interpolation where we are in the future going to allow the user to do something like a complete square. What if the user wants to define an entire square all at once without having to do the individual segments? So how do we, on the other end, segment that in a useful way so we can create a trajectory for the vehicle? So what we do in the gesture system is we use a leap motion controller. So it's in the picture that you see on the left, and it has infrared cameras, and it can track hands up to 200 frames per second. And it gives you about 150-degree field of view, and it gives you about 8 cubic feet of working interactive space. And it's actually able to track all the toys in your hand, but for simplicity, I have it only tracking your palm. So this is the framework of the gesture node, and so what happens is that, as I mentioned, we have those three types of flight paths. And for most of this work, we focused on the formation, so I'll just walk you through that part. So what happens is that in the formation module of the gesture node, we go ahead and characterize the user's input, and I'll tell you how we do that a little bit later. And then we allow the user to do this as many times as they want. Once they're happy with it, that information is sent to the interpreter node, which we'll explain a little bit later. So there's a library of gestures that the user can utilize. These include more simple things like forwards and backwards, and then all the way down into slightly more complicated things like circles and spirals. So how do we go ahead and characterize our gesture input? Because maybe the way that Lauren does a forward is different than the way that I do a forward. And so the way that we do this is I created a linear SVM model. And what this does is it takes features or interesting aspects of our data and goes ahead and maps this information to a space where we can separate the features based on classes. So for example, if you see the picture in the bottom left, we have features that are pluses and features that are minuses. So we could possibly draw a line, as we see in the picture, to segment out the plus class and the minus class. So obviously, with the increased number of features and increased number of classes, this gets exponentially more complicated. And so what I did was I trained our model on 11 subjects last summer, and I take 10 samples per gesture in the library for each of those subjects. And I use things like the hand movement direction throughout the gesture, as well as the eigenvalues associated with the raw data of those gesture movements. So I'm going to hand it over to Erica.
Thanks. So in conjunction with Meghan's gesture work, I also worked on the speech portion of the natural language node. So I'm going to walk you through exactly how the speech works. We utilize a tool called CMU Sphinx, which is software that's been developed over the last couple decades. But the great thing about it is it's free, but also that it's open source. So we're using a Java implementation of it, and we can really get into the bones of how it operates in order to make it suit our needs. One of the ways we did that was we created an application-specific dictionary. The software itself can recognize most of the English language, but because it's searching through a dictionary of a lot of words, it takes it a long time. So in order to speed up the processing power, we gave it a dictionary of a little less than 100 words that were specific to our studies and this application. And I don't know, it's a little small. Yeah, so the way that the dictionary works is it takes English words in the orthography that we're used to, like hello, spelled H-E-L-L-O, and it correlates those letters with specific sounds the way it's pronounced in English. So you can see that the E in hello is pronounced more like an E-H, and the O at the end is pronounced more like an O-W, O, with a little glide at the end. So the CMU Sphinx dictionary encodes it E-H-L-O-W, and that helps it better recognize that sound. Anyone here familiar with IPA? We also have the International Phonetic Alphabet transcription of hello up there for you. This dictionary and these pronunciations are based on everyday speaker patterns, and there is some variability to this. Those of you who are familiar with a Southern accent know that sometimes words can be pronounced differently, even with geographic variation. So there are multiple pronunciations available to us in one dictionary. The picture's a little small, but it shows that we have circumference up there available as circumference and circumference, entirely different number of syllables at that point. So this gives us a lot of power in word recognition, but we also have an application-specific grammar. And the grammar that we have allows us to determine what words should appear in what general order. So we can determine the difference between something like fly forward versus fly the numeral 4 in the word ward. Both might be pronounced very similarly, but one makes much more sense in the context of defining flight trajectories. So utilizing this dictionary and grammar, the speech node takes in an utterance, and then it tries to classify different groups of words. So we have, you can have a single number like 10, but you can have multiple numbers like 115. You can have numbers with decimal points like 115.583. And then you can add a unit to that, 115.583 feet. So now we have this like multi-word group that we can classify and understand what it means. We can also add a qualifier to it like radius, height, circumference. And now we can start actually getting usable data from the speech utterances. We can take the gesture formations that you saw in an earlier slide and determine what type of speech data we're likely to get. So if we hear something like forward, we're probably looking for direction a length of the forward, but not really a radius, probably wouldn't fit. But if you hear spiral or circle, we're going to look for those additional aspects, radius, circumference, height. The speech software also tries to ignore extraneous speech commands. If you cough in the microphone, hopefully it won't translate that as actual speech data. And then we also assume that at the end of each utterance you finished a command. So if you say fly forward 15 feet, it assumes that's one command, processes it, and hands it over to the interpreter as is. You can do it as many times as you like. So let's talk a little bit about that interpreter node and what it's actually doing. The interpreter is responsible for taking the gesture data that defines the shape that we want to fly, as well as the speech data, which defines the extra characteristics of that speech, puts them together in a usable manner such that we can create a trajectory. So you'll see here, if we want to fly diagonal forward right, that we may also want to define how long that forward right is. So it takes the forward right from the gesture, combines it with the 30 feet from the speech, and outputs an actual trajectory from that. So we're going to talk a little bit about our user studies now. We wanted to see, having built this Holy Grail system, how users are actually using these interfaces, how they interact with them, what ways we can improve them, but also what aspects of these interfaces enable people to better work with these machines. So our initial user study plan was to have users use both a mouse interface and one natural language interface, either gesture or speech. Half of our subjects would start with mouse, half would start with a natural language interface. And we asked them to create 3 different flight paths. And a flight path would consist of 3 different formations that you saw in an earlier slide. The flight path order was randomized. And each flight path also included 1 right segment. So we had some standard between all the flight paths for comparison. And then we took data on how users generated these flight paths. We took data on correctness, we took data on time, but we also asked our users to complete background questionnaires, subjective questionnaires, and then ask the TLX. So it would give us some quantitative data on some more interesting components of how these interfaces work. So these are the flight paths that we asked our subjects to create. You'll see each is comprised of 3 different formations. In the first one we have right, followed by forward, followed by left. And then it gets progressively a little more difficult where we include diagonals, circles, and then eventually spirals. Subjects were presented with these formations as is and were asked to read the flight paths and then recreate them using the mouse, speech, or gesture interface. The mouse interface like this, it opened up a window with a drop-down, and the drop-down had as options all 12 possible formations. Users chose one, and they were given a visual representing the item that they chose, and then asked if they would like to continue. If they wanted to continue, they were taken back to the initial screen with the drop-down menu, and they could enter another one. If they did not want to continue, the trajectory would be generated based on what they had already entered.
Okay, so I'm going to give you some more information about the mouse gesture study that we did. So this study included 13 subjects. And so as Erica mentioned, the way the mouse system worked is that you were able to pick a formation and then you would have to click yes or no for if you would like to add more segments or if you would just like to see the final trajectory. And as unlike the mouse, what the gesture system did is that it allowed the user to perform a gesture to represent each trajectory segment, and then instead of having to click yes or no, the user would then swipe left for no, right for yes, and they would be able to continue or not continue in that way. So this is a video of someone using the system. So the way that the system works is that the user would perform their first trajectory segment. So in this case, Erica performed a forward right, as you can see. And then she's going to go ahead and swipe to the right and say, yes, I want to add another segment. And then she goes ahead and defines her second one. In this case, she chose to do a right. And the system characterizes that and shows some feedback image to the user every single time. And then she's going to add one more. And in this case, she's going to do a spiral. And once again, the system characterizes the spiral, shows an image. And this time she's going to say, no, I don't want to do it anymore. And the system shows some combined visual flight path for the user. So that's the way that the gesture system worked and how the users interacted with it throughout the user studies. So here are some preliminary results from our user study. So just taking a look at the user background, about 23% of the users had flown UAVs prior, so less than a quarter of the population has had experience doing anything with flying vehicles. And so what you can see from the results is that from the mouse interface, if you're looking at overall correctness of the flight path, so this means that the user didn't accidentally add extra segments, they didn't accidentally make mistakes in individual trajectory segments or anything like that, or it didn't get misclassified accidentally by the system. So in the case of the mouse interface, the user got 97% correct from the flight path that we have them generate. And in the gesture interface, they got about 41% correct, where they got another 41% misclassified or defined incorrectly by the system. There are other errors, like the most of the error from the gesture interface came from combinations of errors. So the user making some kind of human error where they added some extra segment, or they ended early, or and then in combination with the system misclassifying them. So as you can see from this slide, it may look kind of bad, but it's not, because if you think about it, in a very short amount of training time, the system, the gesture system, is able to classify the gestures correctly 41% of the time. That's pretty remarkable, considering that it was only training on 11 users, one of which was not the user who was currently using the system. So if we look at this slide, let's look more closely at each flight path. So this is looking at the flight paths as individual segments, not overall, did they add an extra segment or anything like that, just looking at percentage of the flight path that they got correct. So as you can see from the mouse interface, the people tend to get it right most of the time, 100% of the time, because they were familiar with the mouse, it was easy, there was just a drop-down menu. But if you take a look at the gesture interface results, you'll see some really interesting results where the people actually were able to get the flight paths correct more than 60% of the time. So on average, if you look at a user, they were able to get the segments correct more than 74% of the time. That's pretty amazing, considering they had very little training time, and they've only used the system at that time period. Most of them had never used a gesture system before. And although the users got the segments correct more than 74% of the time, it was interesting to see that they were still inclined to say that in this case, the mouse interface is what they would prefer to use. And for this case, that makes sense, because they're doing only segments, they're not providing extra information to the system, so it's very easy to use a mouse interface and just pick from a menu which one they want to do and have it added together for them. So let's take a closer look at some of the correctness results. So these two graphs show the percent of the flight path that was correct per user. So as you can see from the mouse when they get it right 100% of the time, but if you take a look at the right graph, you can see that every user except two, I believe, got more than 50% of the flight path correct. And every user but one or two, or I think three, got it right more than 70% of the time. So that's really interesting to see for us. So some basic observations. The hardest part of learning the interface I saw was the timing of the system. So there's an innate timing related to the system because of the way that it was programmed, and that was the hardest part for the user to pick up, which is understandable. And although most of the users got more than 70% of the flight path correct, they were still more inclined to say that they would prefer the mouse interface. And one of the last major things that I observed was that a lot of subjects tended to change the way that they use the system between training and testing. So a lot of people trained on the system, they did it a certain way, they felt like they wanted to sit versus stand. And then as soon as I said, okay, great, let's look at some test cases, they immediately changed the way that they use the system. So some people moved the sensor to a different location, some people sat versus stood, which was different from the way that they were training, and some people even forgot the order in which the system was created. So they were training on the system for at least 10 minutes, and then all of a sudden when they had to do a test case, they forgot, like, oh yeah, there's a message window in between, I have to remember to say yes or no, or I have to remember that I have to add the segments individually, things like that, and that was really interesting to see. So I'm going to hand it over to Erica to talk about the speech study.
So the speech study worked relatively similar to how the gesture one worked. We had the exact same mouse interface that Meghan used in her study, and then the speech interface was designed to mimic that mouse interface, and that it allowed you to say one of the 12 segments, one of the 12 formation possibilities. It showed you an image of whichever one it understood you to have said, and then it gave you a yes/no dialog box for if you'd like to add another. This time, instead of swiping or clicking, you would say yes or no if you wanted to continue. We have a demo here of how it works.
Forward, right?
Megan selected forward right and sees an image of what it understood, forward right in this case.
Yes.
She tells the system she wants to continue. And now she's selected right, which the system understands.
Yes.
And now says she'd like to add another segment and says spiral. The system shows her an image of spiral.
No.
This time she tells the system she wants to end, and the system gives her the full flight path. Okay, so we'll look at a few statistics from the initial observations of this data. First of all, it's worth noting that around 75% of the people who came in had experience with some sort of speech-to-text interface before, most in the form of Siri or OK Google, but talking with their phones. So this was an interface that users tended to be a little more familiar with than the gesture interface. But what we can see is that we actually had the exact same number of percent correct for mouse and speech interface. That is, users got the same number correct for the mouse interface as it did for the speech. However, the errors for the speech interface tended to be, there was some system misclassification and misidentification, which was absent with the mouse interface. With the mouse interface, the errors tended to be adding one extra segment too many. So if we look at the flight path specific data, we can see that with the mouse interface, the only flight path that users got correct 100% of the time was flight path B. And in the speech interface, that's actually the flight path that users perform the worst with. And generally, this was misclassification. This was a flight path that involved a diagonal forward right or forward left. And the system often classified it as backward instead of forward. But you can see that the average total segments of flight path correct for the mouse was now 97%, whereas with the speech interface, it's down to 85%. So despite performing relatively well and with an overall correctness comparable to that of the mouse interface, users tended to prefer the speech interface to the mouse less than they preferred the gesture interface to the mouse. They actually like the speech interface the least of the three that we've looked at so far. And here's some graphs for you to look at. On the left is the percent of flight correct for the mouse interface, and on the right is for the speech interface. You can see, generally speaking, users tend to perform well with both. However, they perform better with the mouse. So some general observations. Despite performing really well with the speech interface and just about as well as they did with the mouse interface, users tended to prefer the speech interface less. And this might speak to some level of lack of trust in the system, a lack of familiarity with the system, and a lack of acceptance of the interface. This is something that we as interface designers can work to improve in the future. And then flight path B tended to be the most frequently incorrect for speech, and that says that maybe there's something we can edit in the grammar or in the dictionary or in some way that the speech is processed to make this easier for the system to understand. Making that correct more frequently might help to increase trust further in the system and get users to adopt this more readily. Additionally, one of the things I noticed in this study is that when users started talking to the machine, they began to over-enunciate their words. This is common. This is very, very common. We think machines don't understand language normally, so we should talk a little more precisely. That way it can be sure to understand what I'm saying. But all of the CMU Speaks tools have been trained on regular, non-over-enunciated data. So all of a sudden, the phonetics of what we're saying no longer lines up with what the dictionary is expecting to hear. And we can combat this in one of two ways, right? We can change the data such that it expects to hear the over-enunciated speech that machines tend to receive from humans, or we can work to train the human to talk more normally with the system. Depending on what the application is, one way may be better than the other. But we'll take a look at the multimodal input user study that we performed as well. This one was a little different. We didn't compare it directly with the mouse study. However, we carried it out in such a way that we can compare these results with the mouse and gesture study and the mouse and speech study that we had carried out previously. We used 12 subjects for this study, 1/3 of which had participated previously in Meghan's gesture and mouse study, 1/3 of which had participated previously in my speech and mouse study, and 1/3 of which had participated in neither study. This helps us determine if there's any effect on additional training in either the speech interface or the gesture interface on how well users performed with the multimodal interface. So the gesture interface was used in this study to define the shape of the segment that we wanted the UAV to fly. And the speech was used to define geometric features of the segment, how long they should fly, how wide the radius should be of the circle. We have a video of someone carrying out this study.
Fly forward, right, 10 meters.
You see she's given the gesture command of forward and provided extra speech information.
Yes.
And tells the system she'd like to continue.
Fly right, 5 meters. Yes. Fly in a spiral, 5-meter radius, 10-meter height. No.
This time she tells the system she's done, and the system gives her the final trajectory based on her gesture and speech inputs from before. So we have similar data from the multimodal study as we had from the gesture and speech studies. So it's interesting that both the gesture and speech correct rates were lower for the multimodal than they were for either of the independent studies. This is probably a side effect of having to use the two different interfaces in conjunction. Most of the errors for the speech system tended to come from some sort of human error, incorrect input, additional segments, but there was certainly some misclassification, around 14%. We see a similar misclassification error rate in the gesture study, around 33%, but we also see some human error. This time it tended to be in combination, either humans, subjects, added one extra segment, or they ended a little too early, and in addition to that, they made some sort of error in the gesture that they provided. But interestingly, with our multimodal study, we saw an error that we hadn't seen in either study independently, and that was a human tendency to combine different errors all at once. And this is largely probably because of the amount of tasks they were asked to do all at one time. We saw an increased frustration level with the multimodal study. However, users did say that they were likely to use this type of interface again, and overall their impression with it was not wholly negative. Anything you want to say about this? So we'll look at some of the flight paths independently. Again, we don't see a 100% correct rate on any flight path, but overall the gesture correct rate was for individual segments of the flight paths was around 66%, and the speech was around 74%. Each of these are about 10% lower than what they were for the gesture study independently and the speech study independently, but both of them are above 50%. So bearing in mind that neither of these studies are trained on the users who actually use the system, these are relatively high success rates, especially when we ask users to do so much at any given time. So in summary, this fully functional multimodal natural language framework actually worked for defining trajectories. We had some success. And this allowed users to use two modes of natural language in conjunction, which is something, I don't know if you've seen me gesticulate a lot of here, but it's something we do naturally. So this really allows us to target a new way of allowing machines to understand a very intuitive way of interacting. We got a relatively high correct rate for both the speech and gesture. Overall, the multimodal system hit about a 60% correct rate. And again, that's greater than 50%. Most of the time, we're getting these flight segments correct. And most subjects say that they're likely to use the system again, which is good. Now that we have more data, now that we can improve the system based on how users actually use this interface, we can make it even better, and people are willing to try it.
Okay, so I'm going to close out with how we can use the system in the future. So this is the image that I showed you earlier in the presentation. And what I want to note is that in the future, what we're interested in doing is taking it to the next step. So now that we're able to define, say, a complete flight path, which includes things like point-to-point and formations, how do we allow the user to take on more of a mission management role? How do we allow them to utilize this natural language system in such a way that they can do things like, hey, now that I know that there's an area of interest somewhere, how can I create a team of available UAVs and then send them to that area and tell them to do something interesting, like map the area some more, take some additional sensor information, maybe even fly in a specific posture feeding pattern or something like that. So how do we take the system that we have currently, give the user more of an integrated, augmented reality type viewpoint, and then allow them to do real-time mission management with that. So that's where we're going in the future. So some specifics about our future work. For the gesture system, what we're looking at, as I mentioned before, is more of a segmentation type thing. So for interpolation, what we want to do is we want to allow the user to define complete flight paths all at one time without having to do individual segments, and allow the system on the back end to do the hard part of segmenting that into individual slices so that we can define that trajectory in such a way that we can make sure that it's flyable, make sure that it's stable, and things like that. And then we also want to go ahead and extend the gesture library to include things like not just spiral up, what about spiral down, spiral forward, things like that. Thirdly, we want to extend the system usability to alternate objectives. So that's what I was talking about in the previous image, where now that we have defined this flight path, how do we allow the system to use the gestures to do things like, hey, there's something of interest over there, I want you to go over there, or I want you to fly in a pattern like this, kind of thing. How do we use the gestures to do that more intuitively for the user? And then lastly, as I mentioned, is we want to take on more of this mission management role where we're allowing modification in real time. So we want to, after defining something, allow the user to say like, hey, actually, all of a sudden, there's something, I've like defined a flight path, but like I'm not really quite happy with it. How do I go ahead and just like pull down some part of it and change the shape of it in real time without having to go back through the entire flight path generation part that a lot of you were using in our user studies. Eric, you can talk about the speech.
So, so for the speech, one of the things that we like to do going forward is to incorporate a lot of the data we gathered from these user studies in order to make a better system. And one of the ways we can do that is creating a more flexible grammar. Instead of forcing users to say 15-foot radius, we can allow both 15-foot radius and a radius of 15 feet. And this way we get at a more natural way that users want to define what a radius is for this type of formation. But we can also handle extraneous speech better. Sometimes users would repeat a command for the gesture system and repeat the same command for the speech. But now the speech hears it as two separate commands, and how do we handle that? So there needs to be some way to kind of error check for duplicated commands on the speech end. But it should also be better at filtering out extraneous noise. When we laugh at something that's happened in the room, the speech system may hear that as some sort of command, and that's no good. So we need to do better at filtering to just the commands that we're interested in hearing. In addition, the system needs to be better at giving feedback to the user, and this is something we can work on going forward. There has to be a way to provide feedback on the correctness of the speech without overloading the user, forcing them to read another message. And this could be visually, it could even be orally, if that works best. In addition to future work for either the gesture system and the speech or the speech system, we have future work for the multimodal system as a whole. And one of the things we really want to do with this multimodal system is generate the next generation model that actually allows for full mission management rather than just the generation of these trajectories, rather than just defining the flight paths that a lot of you saw in our user studies. Now we can define general commands, and this may include such abstract concepts as dices, fly over there. And in this case, the speech command is lacking the specific location of where there is, but the gesture command pinpoints it for you. So we're verging into territory where the speech doesn't give enough information on its own. The gesture doesn't give enough information on its own. We really need to leverage these two interfaces together in order to get at what the human is trying to get across to the drone.
Okay, so that's pretty much all we have for you. This is a picture of our Holy Grail team, and Erica wasn't there, so we had to include her. She left us for 2 weeks for vacation, but I just want to acknowledge Danette Allen for being a great mentor this summer and really helping us to nail down this Holy Grail concept. And I'm really excited about where this is going and what we're going to work on in the future. And I also want to say thank you to Anna Trujillo, who couldn't be here today. She's at a conference, but she was a lot of help on this natural language aspect that we're working on. She does a lot of human factors work, and it was great to kind of hang ideas off of her and talk about the user studies. And I want to thank the entire Holy Grail team by making this come together for us, and also the rest of the AI team for their support throughout the summer and us bugging them all the time about how do we get things on Git or like not break code. So we had a great summer. It was a lot of fun. We learned a lot. With that, we want to say thank you for listening. And that's the end. And we can take any questions if you would like.
Great, thank you. All right, anyone have any questions for Megan or Erica, or did they just answer them all?
Those were awesome.
Well, I'll ask a question, because I think for both of you, this was probably the most significant user study you've ever done.
Yes.
Any thoughts? What did you learn from setting up and conducting user studies, and just general comments?
There's a lot of background things that you need to do before ever talking to a user. There's a lot of work that goes into setting everything up, making sure you have all the paperwork together, making sure you have the space set up, and then deciding how you want to conduct your experiment is actually more challenging than I originally thought. Deciding what order to give information in, deciding when to allow the user to give feedback is like, it can really change the outcome of the study. And like, that was something that I had never dealt with before, and that was really interesting for me.
Great.
I think one of the difficult things that we noticed was if you design a user study, try not to put it on 4 separate computers in one room because it has some sort of run.
All right. Anybody else? All right, Lisa.
So for the speech with the over-enunciation, do you think as users, do you think that's an algorithm or a human thing? As humans use it more, are they going to, as we use those systems more, we over-enunciate?
Repeat the question. Repeat the question.
Oh, sorry. So the problem that we have with over-enunciating when we start talking to computers is that something that we should try to compensate for algorithmically on the computer end. Should we try to compensate on the human end more? How do we go about dealing with this problem? And that's a really interesting question that I think has to end up being application specific, right? When you have a small dictionary of only 100 terms, you can certainly fit in there the over-enunciated phonetics of these words really easily. It doesn't take very long at all, right? And now you've made a system that's usable by people who want to talk naturally to the computer or people who want to over-enunciate. Great. But if you have an open-ended system with the entire English lexicon as its dictionary, it's just like computationally explosive at that point. You can't fit in all of the different pronunciations, all the different dialects and geographical variants. It's just not possible. So at that point, it's something where you hope the user eventually starts becoming used to the system and compensating. Additionally, one way you can go about allowing for more types of speech variation is training the system to interpret multiple different pronunciations in the same way. But training can introduce new errors into the system where you start like overfitting to certain data sets. And so it's a whole other ball of yarn if you want to tackle that. I think probably for this specific application, one of the best ways we could handle it would be to add different pronunciations to the dictionary. But it's because the dictionary is very small in this case.
So one of the other things that we can run into in the speech system is that we didn't really talk about this, but depending on your cultural background, the order in which you say things naturally can be very different. So the American version of English has a very different order sometimes than the British-based English, right? So people who grew up in the UK or even India, right, may say things in a different order or may even use different terms to explain the same thing. And that's something that we haven't really dealt with and that can exponentially complicate the speech classification. And that's something that we're hoping in the future, at some point you have to just assume that you can train your user to a certain extent to sort of compensate for things like that, because there's like an exponential number of ways that someone can say something. And at some point, you have to train your user a little bit, right?
And you spoke to it a little bit with the fact that the users can start to interact differently.
Exactly.
If they notice things work or didn't work, or even from the training to the testing.
Exactly.
So we automatically adapt.
Exactly.
Which speaks to the training. So you're training the human just by using the system, and you become more comfortable with it. So I think.
Exactly.
So thank you.
All right, well, thank you guys. Great exit
Thank you.
presentation.